Okay, so welcome, and today we're going to talk about hydrostatic force and pressure, and then we'll continue on and we'll introduce another theorem and we'll get some examples. So let's start with the idea of what hydrostatic force is. Hydrostatic force is the force that is applied to an object by water. Okay, typically when we talk about hydrostatic force, and again it's standing water. Static means not moving, right? So hydrostatic force is the amount of force that water is putting on, or a fluid, to be more general, is putting on an object that is submerged. So let's take a real simple example of a plate. So let's take a horizontal plate that's at the bottom of, let's say at a certain depth underwater. Okay, well, the force that's acting on the plate is really the area, right? And it's the amount of water that's above this area. Okay, so to find the force, we take the area and multiply by the depth, right? The depth that it's under. So we find the volume of water, right? So it's the volume of water that's right above the area of the disk, right above the area. So it's the area times the depth. So we get this volume, right? And then the force is going to be, we multiply by the weight density of the fluid or water. And so that gives us the hydrostatic force on the plate here. Okay. Now the hydrostatic pressure is then just force per unit area. Okay, so force per unit area is pressure, and so that's where we get just rho s. Okay, because the areas divide out. So that's the difference between hydrostatic force and pressure. Now in the English units, the units for pressure is what we call pounds per square foot, okay, or PSI, which is pounds per square inch, which is very common. In metric system, we use the units of newtons per square meter, okay, so which is units per square, or newtons per square meter. Okay, and so that's what we use in those cases. Now, the other unit for pressure that's also used is pascals, which is, instead of saying newtons per square meter, we call it a pascal. Okay, so 1 newton per square meter is a pascal, 1 pascal. 1,000 newtons per square meter is what we would call a kilopascal. Okay, so now that you have the idea of what it means, what a hydrostatic force and pressure means, now there's another principle by Pascal that we're also going to use that's going to be very helpful, is that the pressure is the same all around the object. So the pressure is equal all around. When it's submerged in liquid, it's going to be all around, the pressure is the same. Okay? So it doesn't matter whether this plate is horizontal or vertical, the pressure all around it is the same. So why is it important? Because it's going to give us a way to figure out the hydrostatic force on an object, for example, like a dam. Okay? So the only thing we have to consider is the depth, because if we hold it horizontal, like in this case, well then depth changes, right? So depth changes in this case. So that's where we're going to have to be careful, okay? But the idea is still the same. So now let's assume that we do have a disk. Let's say we have a thin disk, a plate, and we have it submerged horizontally. And we want to calculate the hydrostatic force on the plate. Now, if it's horizontal, that's easy because the depth is the same, and so all you do is use this formula, you're done, boom. So it's a straight multiplication. But when it's horizontal, now the force on the plate is changing based on the depth. So we've got to also the width, right? The width is also changing. So there's two things that are changing. The depth and the width of the disk. Okay, so the area is changing, right, in two dimensions, right? The depth and the width. Okay, so we're going to have to consider both of those. So let's start deriving how we would find hydrostatic force in this situation. Well, let's take this example, and this is a general example. So, and again, orientation, your reference frame is important, okay? So in this case here, I put the plate above, or excuse me, below the water surface, right? You could put it at the water surface, but let's do more general. Let's say it's submerged below water, below the surface of the water. And we know that the diameter is from A to B, right? So the top edge of the disk starts at A and the bottom edge of the disk ends with B. And so what we want to do is we want to find the hydrostatic force that's on this disk. And so what we're going to do is we're going to subdivide this interval into subintervals, thin strips of the plate. And so what we're going to do is we're going to consider one of those subintervals. And again, we're going to take a sample point, because what we're going to do is we're going to assume if it's really thin, right? We're assuming really thin strips of the plate. So we're going to assume that the depth is considered like constant, okay? So we're going to take a sample point, x sub I star, and we're going to calculate a function that represents depth. That's going to be s, right? So s sub x sub I star. And then the width, the corresponding width of the disk is going to be w x sub I star, of x sub I star. And so how are we going to use this? Well, we're going to find the area of this strip. So we're going to basically treat it like a rectangular strip, okay? Because if it's thin enough, it'll be close enough for approximation purposes. So in this case here, we're going to what? Let me erase this. We don't need that right now. And so what we're going to do is we're going to write a formula for the area, right? So the area in terms of x sub I is going to be length times width. So it's going to be s sub I star times the width okay. So now, what do we do now? Well, let's use our formula, right? Now, if we use the formula, so here's the formula for force, so now we're going to basically plug in here. Oh, hold on a second. No. I messed up. Nope, that's not right. Hold on. Area, I keep forgetting. Right here. We got this little width, right? So it's the length, right? If we look at this like a rectangle, it's going to be the length of the rectangle. That's your W sub xi. So that's W of x of I star. But what I forgot was, again, the width of the strip is the distance between x of I and x of I1, which we know is what? Delta x, right? It's, remember, regular subintervals. So that's our delta x. So this is the area. Okay, I got ahead of myself. Okay, so now we've got our depth, which is represented by this. And now we're going to put these together. And this is constant, right? So now if we wanted to use the force, and let's call it F sub I, or no, not, do we want to do that? F. Yeah, F sub I equals rho times A of x of I. Yeah, oops. And then this is going to equal rho W so x of I star times delta x times S sub x of I star. Okay, there we go. So now there's the force formula. So now all we have to do now is add the forces for each one of these. So again, if we have n subintervals, so this is just for the ith interval. So now we got to sum them all up to get an approximate force. So now our force can be approximated by the sum of rho times W x of I star times S of, let's do this, of x of I star delta x as I goes from 1 to n, okay? And of course, we can use our Riemann sum, right? This is a Riemann sum, so we can take the limit and get the exact force. So the exact force then becomes the limit as n approaches infinity of the summation as I goes from 1 to n of f sub I, right? And so what happens? This becomes an integral from a to b of rho times W of x times S of x dx. And so this, evaluating this integral gives the force of the plate, on the plate. Okay, and so just like before, when we're talking about problem solving, we're going to give you the steps for problem solving for these types of examples. Because again, it depends on the shape, right? So if I put a different shape in here, you're going to have the different function for width and height and so on. So in the next video, I'm going to just go through the steps and then we'll do an example or two. Okay, take care.